Hello students, the topic that we will be looking at today is divide and conquer strategy. This technique is primarily used to solve multiple type of problems including some sorting algorithms, binary search, convex hull, finding maximum and minimum values. To begin with, let's try to define what exactly we understand by divide and conquer strategy. The idea here is to basically break down a large problem into smaller subproblems that are similar to the original problem, then recursively solve the subproblems and finally combine the solutions to solve the original problem. Because divide and conquer solves subproblems recursively, each subproblem must be smaller than the original problem and there must be a base case for subproblems. At each level of recursion, the following steps need to be applied. The paradigm, what we call as the paradigm of divide and conquer. One, we basically try to divide this problem. So you may use the word divide or split the problem. Let's assume that the size of the problem is n. So we have a problem of size n, and this problem will then be basically divided into a subproblems. And the size of each subproblem that has been divided will be n by b, where b is any value. Remember in this case that we need to make sure that the value of e is necessarily greater than 1, because if we keep the value of b smaller than 1, then in that case the actual problem will not be divided into smaller instances. And the number of problems that will be created, that will be a subproblems where a can be greater or equal to 1. Once we have divided that problem of size n into a subproblems, what we try to do is that we try to solve these individual problems. Here in this particular step, the subproblems are solved recursively. If they are small enough, solve the subproblems as base cases by doing exhaustive search. So let's take an instance, for example. This is my problem of size n. Using divide and conquer strategy, I'll try to divide this problem into smaller subproblems. Now what you need to understand over here is that the problem size of these subproblems will be smaller than the original problem, but the type of problem cannot change. The type of the problem has to remain the same. Say for example, if we are basically trying to solve a searching problem, if this is a searching problem, and let's suppose we are searching in an array of size 10. And I divide this problem into two subproblems, then the size of the problem will get reduced. Let's suppose by n by 2. So each of the subproblem will be of size n by 2. That means we have 5 elements of array in this case and 5 elements here. But the fact is that even these subproblems, they are also of type searching. So the type of the problem will not change. So once we divide this problem into multiple steps, we can further divide it till we reach the base cases. These base cases are basically then solvable using exhaustive search. Once we have completed this solution, we move to our third step, that's combine or merge. Now you remember in this case that there are some problems in algorithms that require this particular step of combining or merging. What is combining or merging? It's very simple. You have a bigger problem, you divide it into subproblems. You create smaller problems out of these. Now when you solve these smaller problems, then you try to combine the results back so that you get the original result, so that you get the original solution for the actual problem. Say for example, if we take the case of searching here. I'm taking the example of searching. In searching, the idea here is to basically look for a particular element. Now remember that if I found that element, I do not need to combine those results. I do not need to merge those results back because my job is done when I search a particular element. But if I'm trying to sort certain elements, so once I divide that problem, then I need to combine them back so that I put them original array, which is a sorted array. If we talk of efficiency, in terms of efficiency for this, the same problem, the entire divide and conquer problem, can be represented using using the recurrence relations. Say for example t of n. Now remember in this case the t of n is the running time of the problem that we are trying to solve over here. So what we can say that a times, this is the number of subproblems that we are creating out of this original problem. A times t of n by b. So these are the smaller problems that we have created. So n by b over here will basically indicate the size of the problem, while as a will be the number of subproblems that we are trying to create, plus some work done for the merge part. That's what will be including the merge part over here in this case. These type of problems you can basically, if you remember in unit 1, we had discussed the method of master theorem. These type of problems can easily be solved using master theorem. So this is divide and conquer strategy. If I had to put the algorithm for this divide and conquer strategy, the algorithm will look like this. Let's have a look at the algorithm first. So if this is the function I am using for divide and conquer, and this is the problem that I am trying to solve using this particular strategy, what we will do is that we will first check the size of the problem. If my problem is small enough that it can be solved, then we will simply return the solution of this particular problem. So if the problem is small enough, just return the solution of the problem. But if the problem is not small enough, then we may need to basically divide it further into smaller instances so that we can solve those smaller instances. In case my problem is not small enough problem, then I'll be dividing my P into smaller instances of P, smaller subproblems. So let's call those subproblems as P1, P2, all the way up to the number of problems that we need to create. So these are the smaller subproblems of the same problem P that we are trying to solve in this case. Now once we have divided this problem entire, we'll apply the whole operation again to these subproblems now in this case. So apply D and C to these subproblems in this case, to each subproblem. We'll continue with this procedure till we are able to divide the original problem into smaller subproblems which are smaller enough that they can be now solved. Once we are done with the division part of this, what we will try basically is that we will try to combine the results that have been that is returned from here. So this is the combination part of this. Now remember in this case we are trying to perform 3 steps. Step 1 will be trying to divide the original problem into smaller subproblems. Once these problems are smaller enough, we will try to basically solve these smaller problems. And once we have solved those subproblems, then we will try to combine both all of those subproblems into the original solution of the problem. So this is the algorithm, how a divide and conquer strategy works in this case. Let's try to find out how can we solve the problem of binary search using divide and conquer strategy. Before we actually try to solve this problem using divide and conquer strategy, let's try to understand what exactly the problem is. Given an array or a list of elements, we need to look for a certain element that we are trying to find. There are different techniques of locating that particular element. One such technique is what you normally is famously called as linear search. Now let's assume we have an array of size 8. And I'm looking for this particular element 2 in this case. Now using linear search, I need to traverse the entire array till I reach this location. So I will try to take my value 2 that I am trying to look for and compare it with first element 3. Now since this is not the element that I am looking for, I will move ahead on the array and try to compare it with the next element. Using this strategy, I will traverse every single element of this array till I reach the 2. This is where the condition is satisfied and the element that we are trying to search for is returned. The problem with this approach is that if the size of that array that wherein we are looking for the element is very large, let's assume our n is equal to 1000 in this case, and let's assume the element that I am looking at is the 1000th element. So using linear search, I will have to traverse all those 1000 elements. That means the order of the complexity in this case will be order of n. We may sometimes get lucky and the element that we are trying to look for happens to be the first element only. That's the best case scenario. In best case scenario, if it's a best case scenario, then the complexity is order of 1. But if it's a worst case scenario, then you will have to traverse every single element before we actually reach the final element. How does the binary search work on the same type of problem? Binary search has a requirement that the array or the elements that you are trying to basically wherein you want to search, that array needs to be sorted. It has to be a sorted array in this case. So for the same problem, if I look at the same problem, let's do it like this. So elements are sorted in this case. In this case, and let's assume that we are looking for an element 15, which is here. The divide and conquer strategy tells me that the size of the problem is large in this case, right? So what we need to do in this case is that we will divide the problem into 2 halves. We divide the problem into 2 halves and then we try to search the element into each of these halves. So we try to search our element in this case or in this sub-problem. If the size of the problem is still large enough, then what we can do is that we can further divide these problems into smaller sub-problems. We can keep on dividing the original problem till we reach the base case, wherein we can basically find this element that we are looking for. Once that element is found, we'll simply return back. Let's have a look at the algorithm, how it works. There are 2 methods with which we can basically implement our binary search. One is an iterative approach and another is a recursive approach. Remember these iterative approach and recursive approach. Iterative approach is runs with the help of a loop that exhausts all possible options till the job gets done, and the same set of instructions is repeatedly executed. In case of recursive, the function that you are using to execute the set of instructions is repeatedly calling itself. So if I check out the iterative version of this, so iterative algorithm in this case will be binary search. As the arguments, you will be passing the array wherein we are trying to look for the particular element and the value of that element that we are trying to search. So we have an array. Let's say the size of the array is an array of size n, and the value that I am trying to search. Now in this case, this is the array in which we are trying to find this particular element, and this is the element that we are trying to locate. We will be using certain indices in this case. These indexes will be used as a pointers. They will point towards certain locations in that array. So the indexes that we will be using is low. We will simply initialize it to 0. We will be using a high index. It will be pointing towards n minus 1. And we will be using one more index, that's mid. I'll come back to this. Where do I use this mid? Now, remember these are the indices. We'll come to them. How do I use them? In my algorithm, what I do is that I run a loop. The idea of the loop is that I try to traverse all the possible elements that are there in my array. So this low, when I say it's pointing towards 0, that means if this is my array, it has multiple elements. Remember the size here, that's the array size. Low is pointing towards the first element. That's where the 0 comes from. And my high is pointing towards the last element of the array. So once I start traversing, I'll keep a track of the elements that I've traversed by keeping them in the loop, comparing low with the high. So as long as my low is less or equal to high, I'll keep performing these operations. First thing I do is that I'll try to calculate my mid value over here. Now the mid value that you compute in this case is the half of your low and high. So what I will be doing is that my low plus my high, and I divide it by 2. You just need to remember that in these cases we take floor functions. In these cases, floor functions just basically round the number to the lowest, closest smaller number to them. Once I compute my mid value, now remember this mid value is basically is an index. It's a pointer that's pointed to a particular location. I try to look at the value at this particular location. So for my array, now students, remember that the mid here is a pointer that's pointing towards a certain location. A of mid is the value that's at that particular location. I compare that value A of mid with my value that I'm trying to search in this case. If my A of mid is greater than the value, if the value that's pointed to by the mid index, if that value is greater than this value, then I need to understand that the element that I'm trying to look for is in the left half of this. Because of that, I'll try to reset my high to mid minus 1. And in case my A of mid is less than the value, then I will reset my low to mid plus 1. I just need to use the space in this case. I'll be continuing from here. So I've basically checked for both the conditions. I've checked the condition, does the value that I'm trying to look for, does it belong to the left half of the subproblem, or is it on the right half? If it's on neither side, so if it's not on the left side or not on the right side, then there's the probability that I actually have found the element. And I will simply stop over here. In case, the second possibility in this case can be that the number that I'm trying to look for is not present at all, it's not there. So in that case, once I come out of the loop, I will simply return not found. And we will exit. To understand this whole algorithm, let's take an example and try to analyze this whole algorithm using an example. So the number of elements in this particular array, we have 7 elements. So in this case, you can put it like this. Size of the array is 7. So this is my array A. There are certain elements that are present in this array, but remember those elements, that's very important in this case in binary search. In linear search, you do not need the elements to be sorted, but in case of binary search, these elements need to be sorted so that then only it can work properly. So let's suppose we have these elements 10, 15, 20, 25, 30, 40 and 50. Let's assume these are the elements. And in this case, let's say that I'm trying to look for this value 40. So the value that I'm trying to look for, I'm searching, is 40 in this case. So how do I start? I set these pointers, the low and the high pointers. So my low will point to the first position. My high will point to the last position. So low will be, okay, what are the indices of this array? This is index 0, this is index 1, this is index 2, this is index 3, this is index 4, index 5 and index 6. Remember, the indexing of an array starts with a 0 and it ends at n minus 1. So low is actually pointing to 0th position and my high is pointing to 6th position. Now check out the algorithm. What's the first condition? While the low is lesser or equal to high. Is that true? Is 0 less or equal to high? 0 less or equal to 6? Yes, that's true. The moment I see that the condition is satisfied, I go inside the loop and I try to compute my new mid. What's the value of mid in this case? Low, that's 0, plus high, that's 6, and we simply divide it by 2. Since this is an even division, you do not need your floor functions, you get a value of 3. So my mid is now pointing to 3. Once I compute my mid, I need to look at the value that's at this location mid. So my A of mid is actually now A of 3. What's the value at A of 3? A of 3 is a value 25. Now what we will do is that we will compare this value at this middle position with the value that we are trying to search. And the idea here is to look for whether this value that we are trying to search, is it smaller than the value that we are looking, or is it greater? If it's smaller, that means the value that, since it's a sorted array, if it is smaller, that means the value that we are trying to look is in the left half of the array. And if the value that we are trying to look for, if it is greater than this value, then that value lies somewhere in the right half. So that's the comparison I'm trying to perform over here. If this value A of mid, which is basically 25, is it greater than the value? What's the value? 40. Since the condition is false, so it will skip this if statement, it will not go inside this if statement. It will move to the next else if statement and find out A of mid, that's my 25, is it less than the value? Is it less than the 40? In this case, my condition is true, because obviously 25 is smaller than 40. So what do? When this condition is true, I'll try to reset my low. So what's my new low? It's mid plus 1. What's the earlier value of mid? That's 3 plus 1, that's 4. So the next computed mid value is 4. Now remember, what we are trying to do, what we are trying to achieve over here in this case is that I'm trying to basically shrink the space, that the searching space wherein I'm looking at, that space I'm trying to basically shrink so that I take it to a point which is very small or sub-problem, which is a very base case, and that base case can be solved easily. Now because of this action, because of this step, my low is no more pointing at this place. Instead it's pointing to, low is mid plus 1, that's 4. That means my low is now pointing to this place. That's the change. Sorry, this is not our mid, this is our low. Make the correction please. So my low is now pointing towards this location, and this half of the array, since it's guaranteed because of this particular step that the element is not in this part of the array, so we are actually taking this half out. We are not even considering this half. We'll be only looking in the next half. That's the idea behind divide and conquer strategy, that you actually try to shrink the space, you actually try to curtail that search space that wherein you are trying to look for the element. Now we'll go back and check out the condition, the next iteration of the loop. Is my low still less than or equal to high? Now in current scenario, low has a value of, let's redo it here. Now low is pointing towards 4 and my high is pointing towards 6. The condition checks is looking for, is my low less or equal to high, which is true in this case. That's true. So what I will do is that we will go inside the loop, compute the new value of mid in this case. What is the new value of mid? Mid will be current low plus current high divided by 2. Current low is my 4 plus current high is my 6, and I will simply divide it by 2. Again, it's evenly divisible, so we do not need the floor function. My new mid is 5 in this case. Once we compute the mid, we try to look at what exactly is this mid pointing to. What is the value that this mid is pointing to? So we try to look for A of 5. Now in this case, a of 5 is the value 40. Let's look at the algorithm in this case. Algorithm checks for the condition that if is this a of mid, that's 40, is it greater than the value? What's the value? Value we are looking for is 40. Is it greater than 40? No, it's not greater than 40. So we move to the next if statement. Next if statement is checking whether this a of mid is less than this value. So the next if statement will be, this is if, the next else if statement will be, is my 40 less than 40, which again is not true. We can find out, again it's not true in this case because 40 is not less than 40. Then there arises a situation wherein we simply return the mid. Return mid. Now remember, the mid is at this point pointing to location 5. We simply return this mid because look over here. What's happening is that I'm trying to look for this value 40. I can see that the value 40 is not larger than the value 40 in location 5. Again, it's not smaller than this. Then there is only one possibility that it can be, is that it is the element that I'm trying to look for. So because of that, we're using that logic, we can say that we have found the element at position 5. Element found at position number 5. This is how exactly your binary search works. Just in case, let's take another possibility that the element that I was trying to look for, that does not belong to the array at all. In that case, what will happen is that my low, because I'm pushing it, my low will exceed the high, and because of that this condition will become false. Once this condition becomes false, I will simply return back element not found. Not found. Hope this example makes it very clear. The next step we will be trying to do is analyze the complexity of these binary search algorithms. To analyze the binary search algorithm, we need to recall that each comparison eliminates about half of the remaining items from consideration. What is the maximum number of comparisons this algorithm will require to check entire list? If we start with n elements, let's take a scenario wherein I have n number of elements. These are the n number of elements that I am trying to look for. This is a search domain where I am trying to look for my element. At each comparison, remember when I was trying to divide it using that mid pointer, at each this comparison, we try to divide this problem into two halves, each of size n by 2. This is the first comparison, remember that. So I can say on my first comparison, this is a comparison, and this is the division. On my first comparison, I actually divide the entire array into two halves. On my second comparison, I'll actually be dividing this into n by 4, n by 4, n by 4. So each subproblem in this case is of size n by 4 in this case. So for my second comparison, it's equivalent to n by 4. We can continue on dividing or splitting the actual algorithm till we reach a point wherein the problem can be solved. Say for example, for any value I, what is the division in that case will be n to the power divided by 2 to the power I. How did I get this 2 to the power I? It's very simple. If I look at this case, for first comparison, it's actually n to the power 2 by 2 to the power 1. N divided by 2 to the power 1. That's n by 2. In this case, it was n divided by 2 to the power 2. If I take my third case, it will be n by 8. That's n divided by 2 to the power 3. That's 8. Likewise, for some certain number I, it will be equivalent to n divided by 2 to the power I. Now remember, for this case, in n divided by 2 to the power I, when we split the list enough times, we end up with a list that has either just one item, either that is the item we are looking for, or it's not. Either way, we are done. The number of comparisons necessary to get to this point is I. This is the I number of comparisons, where if we see this, n divided by 2 to the power I is equal to 1. That's the one location that we are trying to look for. This may be a successful search, or it may be it may not be a successful search, but this is the element that we are trying to look for. When we try to solve it for this value of I, remember we have a mathematical function that means the same thing as the number of times we repeatedly have, starting at n until we get the value 1, the base 2 algorithm of n. Logarithms are basically inverse of exponentials which grow rapidly. So that if we have log to the base 2n, to the base 2n is equal to x, the logarithm function, if you try to find out the exponent function of this, that will be n to the power of x. That's the exponential of this. Say for example, if I take an example, log to the base 2 of 128 is actually 7. And if I try to look for the exponential part of this, that will be 2 to the power 7. Sorry, I need to make a change over here. It's basically 2 to the power of x. Using this particular concept, we can conclude that the complexity of binary search is order of log n. Remember, you need to understand over here is that this complexity we are looking for is for worst case and the average case. In best case, the element will be the first element that we are trying to look for. That is the first middle element. Then the complexity will be of complexity order of 1. Hope you understand the concept. This is today we try to analyze and understand the binary search algorithm. How do we solve this binary search algorithm using divide and conquer strategy? In the next lecture, we will be trying to solve the max-min problem using the same strategy, divide and conquer. We need to analyze, or we need to traverse through an array to look for the largest possible element and the smallest possible element that is present there in the array. Thank you very much.